graded the midterm, and I don't know where we are in the upload of that. I saw the results, they look actually really nice. It was a very tight distribution of fairly good grades. I don't know if you uploaded already or not.
Michelle was supposed to.
Michelle was, so I don't know whether it is or isn't uploaded yet, but it's about to come. And there's really not much to worry. It is very nice. Okay, that about that. Then we are in the bonus homework regime, but some of you really need to take those bonus homeworks because we saw that some of you have very, very few partners. We uploaded an Excel spreadsheet. I would do so into the OneNote, and then you can see like a cross mesh kind of who submitted homeworks with who else. And some of you have very few partners. So by the end of the class, if you have only 4 partners, then we will only count your homeworks up to week 4. And the rest of those you will just get zeros for that. We don't want that. There is still plenty of opportunity. Originally I thought you should have done it by week 5, having 5 partners, but I will leave that to the extent that if by the end of this course you've had 5 partners, we'll take into account up to week 5. If you have 8 partners, we'll take account up to week 8. Week 8 is this week. Week 8, the Wednesday submitted homework was the last mandatory homework, so 8 partners is enough for a minimum set of homeworks. But of course, I could hope that you continue submitting homework up to the very last Friday of this class, and then get an opportunity to exchange maybe not perfect scores with then perfect scores for the week. Also, the homework which I'm assigning is of course relevant for the final, so there is a benefit you have. But as a reminder, it's only 12 other homeworks which will count towards your final grade, and we'll take the 12 best. And if you haven't already 12 by last Wednesday, then what you did for today's bonus and what you're going to do for the next days is also bonus. Okay. Then we talked about kinetics. We still talk about kinetics for probably 2 sessions after this, so probably until Wednesday, maybe only until Monday. We'll see. And then after that, we are going to talk about transport. That is a very important question as well, but where we need to understand things which are really, really important for governing real-life chemistry. But before we go to transport, we want to be proficient about kinetics. And last time I mentioned that there are different orders give rise to different rate laws. They can be integrated for zeros orders, they can be integrated for first order. For second order, they can be integrated in the special case that you have a stoichiometric mixture of the 2 reactants. Now, if you have the same reactant twice, then it's of course stoichiometric, and you don't have that problem. But yeah, in that case you can. Otherwise, you already did for homework a way of numerically integrating the rate equation. That is what you do with Excel, those homeworks which I'm assigning, numerically integrate. You don't get an analytical formula, something which you can write as a formula over here, but you get something which is a numeric. The numbers are right, but there's no formula really for what you came up with. There's one more aspect which I haven't talked about yet at all, but you probably know that from Chem 1. There are half-life times for reactions. So you can ask yourself, after which time half of my reactant is consumed. And the half-life time is independent on the initial concentration, only for first order reaction. Only for a reaction like radioactive decay, first order reactions. Atoms don't react with the other atoms in order to radioactive decay. You have a half-life time, T1/2, which is given as a logarithm of 2 divided by the rate constant for that. There's no amount of concentration. The half-life time for the zeroth order reaction is given by the amount you have divided by 2 and divided by the rate constant of the zeroth order reaction. And for the second order reaction, it is 1 over K times the concentration you have initially. They vary with the initial concentration. So another test for is my reaction, the first order reaction, would be to see whether the half-life time is independent of the concentration or not. Now then we went through those things last time, and I'm not going to go through them again. I'd like today to talk about slightly more complicated cases. Let's imagine we are looking at a reaction as we looked at the very beginning of kinetics, that we have 2 N2O5 molecules and they decompose into 4 NO2 molecules and 1 oxygen molecule. Or you could write that probably just as well as 1 N2O5 molecule decomposes into 2 NO2 molecules and half an oxygen molecule. What you find from that already, it's kind of ambiguous what is really going on, what is a good way of writing that. And so it is probably a better way to think about elementary reaction steps. There is no way really that those 2 molecules happen to bounce into each other and then as a consequence of that bounce, they unravel into these 5 other molecules. That is, if you think about balls and sticks and colliding and so on, it is very, very hard to conceive that the reaction would really proceed at the atomic level as it's shown up here. Rather, experiments might be done where people investigate, for instance, is there a transient concentration of NO3 in that system? Experiments might be done to figure out what really the elementary reaction steps are. Or in other words, just from looking at the overall reaction, we might be able to guess elementary reaction steps, but we have no way of knowing that our guess is right. We need to have experiment, or these days maybe theory, in order to tell us. But if we know the elementary reaction steps, if some method gave us the insight to see that the elementary reaction steps are N2O5 is in equilibrium with its decomposition products NO2 and NO3, and if NO2 and NO3 react again, they could of course form N2O5 again. But they can also run into each other and decompose into 3 molecules, into NO, O2, and NO2. So what here apparently happens is that an NO3 molecule over here, as a consequence of this collision, falls apart in this way. Maybe one of the oxygens of the NO2 interacts with one over here, or something of that sort. Whatever it is, if you know that this is an elementary reaction step, then you know that this is one of the reactions that proceed. And then here you have a final reaction of the NO2, which was produced over here, reacting with more NO3 in order to form 2 NO2s. So if we know that these are the elementary reaction steps, then the elementary reaction steps directly relate to orders of the reaction. So this is a first order process going forward, it's a second order process going backward. This is the second order process going forward. The third order process it would be if it went backward. But you see the arrow over here, it practically doesn't go backward as a reflection of that trimolecular reactions are exceedingly rare and usually doesn't need to be taken into account. And then over here, it's a second order reaction forward. It would also be a second order reaction backward. But the arrow indicates that that is such an unlikely reaction that we probably don't need to worry about the backward reactions. So the bottom line is we have an overall reaction. The overall reaction doesn't tell us anything about the kinetics of the system. But some experimental theory allowed us to find elementary reaction steps, and those elementary reaction steps are really how the molecule progresses through the reaction, and they tell us immediately what kind of order is associated with them. So in order to figure out how fast this overall reaction is, we have kind of consecutive reactions. Consecutive, reversible, and non-reversible reactions, and somehow need to figure out from these consecutive reactions how fast does the reaction progress. And there are two approximations people used to do before computers came about, and people still do even in the presence of computers occasionally, if otherwise the reactions are too complex, if there are too many steps involved. But mind you, the kind of reactions which we are looking at over here are to a great extent simple enough that we can just put them into Excel and get the results ourselves. So it's not necessarily so super useful what I'm saying here for the kind of reactions you're going to look at in your career most likely, because you can just all put them into Excel and get the results. But these approximations are the foundation of a lot of other chemical insight in various areas of chemistry, and also the subject of tests if you ever go to graduate school or so. And so I feel compelled that I teach them the formal way as well, even though in the end use Excel. So let's talk about the rate determining step first. In the rate determining step, I assume a reaction, an overall reaction proceeds in several elementary steps, first making out of the A's B's, and then C's, and then maybe D's. And one of those steps is slow. That is the bottleneck step. And in the rate determining step approximation, we say, okay, if that is a bottleneck step, then we need to figure out two things. A, how many reactants are available for that bottleneck step? And B, how fast is that bottleneck step? And then maybe after that bottleneck step, out of the products of that bottleneck step, out of that rate determining step, how many products do I get? Just straight geometry. Is it 2 for 1, or 3 for 2, or whatever it is. But in order to figure out how fast that reaction is, I just want to figure out how fast is my rate determining bottleneck step. And once I've figured that out based on how many reactants are available and what's the rate constant for that bottleneck step, then I say my overall reaction is just governed by how slow the slowest step is, and I'm not going to do any more sophisticated calculation. I'm just looking at what is the rate of performance. So I'll take a somewhat different reaction system over here, where we form this azobenzene over here, and I'll see whether we can proceed. So if I wanted to do this, then somebody nicely wrote already, this is a slow step. So if I want to figure out which one is my bottleneck step, it's a slow one, right? It's the rate determining one, it's a slow one. Everything else is faster over here. So if we say that is the rate determining step, then we can say the rate of our overall reaction over here is really the rate of the slow step over there, and that is, we have the rate for the K2 times the concentration of H2NO2 plus times the concentration of bromide. So that is the rate of our reaction. So I'm looking at this complex overall reaction here. So I'm looking at this complex overall reaction over here from here to there, from aniline to isobenzene. Then I will have these individual steps over here. And the rate for this overall reaction is pretty much given by this rate over here. Rate determining step approximation. Just to some complication. I of course don't know how much H2NO2 plus I have. That's not my reactant. That's an intermediate. And so I need to figure out how much H2NO2 I have. And in order to figure out how much H2NO2 I have, I need to look at this equilibrium here in the beginning, because there it is being made. And for this to be an equilibrium, it means the forward rate and the backward rate is the same. Otherwise it wouldn't be an equilibrium. So if the equilibrium establishes itself quickly, then I can figure out from the equilibrium condition over here, forward rate and backward rate need to be the same, how much of the intermediate I have. So I know that the K1 times the concentration of H plus times the concentration of HNO2, that this forward reaction is the same thing as a backward reaction, equals K minus 1 times the concentration of H2NO2 plus. If that were not the case, I wouldn't have an equilibrium. Note that in this case I have it really easy because all the stoichiometric coefficients here are 1, correct? So I would have here 1 over 1 and I have here 1 over 1. If your stoichiometric coefficients are not the same, then you always need to think about where do I need to have the right numbers at these places. Which rate are we really looking at? How do we write this reaction? How is this reaction written? Where is it to? And so on. So what does the rate constant say? We talked about that at length. You will have to do that in your homework, figuring out where those numbers are. Okay, good. Then we have this equation. So this equation, of course, then offers us this one here, and this is what we need here. So what we do is that we say the concentration of H2NO2 plus, this one here is K1 over K minus 1 times the concentration of H plus times the concentration of HNO2. And this is here the formula which we need to bring in here. And so for our overall rate, we are getting that the rate is K2 times K1 over K minus 1 times the concentration of H plus times the concentration of HNO2 times the concentration of bromide, this was here, times the concentration of the bromide. So that is the rate for our overall reaction. Last step, we need to check if I'm going once to this step, I'm getting 1 ONBR, and from this 1 ONBR, I'm getting one product. So it's always all ones in the stoichiometric coefficient. So that we don't need to worry again, putting the numbers for our stoichiometric coefficients right. In your homework, it's not 1. So then you need to figure out that you then say that the rate is given the right way. That the rate over here might have had some numbers associated with it, some stoichiometric coefficients associated with it, if you look at the overall rate. Okay, that is rate determining step approximation. Why is it helpful? It is helpful because now I have this rate equation over here. Still don't have it integrated. Probably can't integrate it in the meaningful way. It's not about that. It's about if I wonder how can I speed this reaction up? I know, okay, I can speed this reaction up by putting more H+, by putting more HNO2, by putting more bromide into it. That way I can speed up the reaction. And in each case, the reaction will be proportional to how much more I'm going to put in there. That is the operational knowledge which you can get out of this. If you want to make this reaction go better, go faster, then you do this or that. That is the knowledge you can obtain. Not a great knowledge, not the knowledge of how much HNO2 do you have as a function of time that would require integrating this one. But probably not possible, given how complex it is. But at least you can see how you can manipulate the reaction, what impact which reactant has. You will find that there will be, on occasion, things which are in the denominator, where you divide with them. And so you'll find that putting more of one reactant will actually inhibit the reaction, depending on how your equations are. That is a rate determining step. In your homework, you have to do exactly the same thing, except that the system of reactions is different. Okay. Next thing is, I'd like to look at the steady state approximation. So in the rate determining step approximation, we were saying there is one bottleneck step, and we need to figure out how many reactants are available for it, how fast that step is, and how the relative stoichiometry is. And that will tell us everything about how the reaction proceeds. In the steady state approximation, we say something else. In the steady state approximation, we say, let's look into intermediates. And let's assume that all the intermediates are in constant concentration. And if we know that the intermediates are in constant concentration, then we can calculate from that what the rate is. So, if I'm thinking in that fashion, then I can again look at the same system. And now, I don't care where is the bottleneck step, at least not in the beginning, and say, okay, the rate of this overall reaction is certainly determined here by the end. The rate of my reaction is that I have K3 times the concentration of O and Br times the concentration of aniline that is the rate of my reaction. This is what gives me finally the product. This is the rate of my reaction. The aniline over here is a reactant. Arguably, I control how much I have of that. It is something I put in the beginning, so I don't need to worry about that. But the ONBR over here is an intermediate. It is being produced over here and then consumed over there. So the concentration of the ONBR, that is something which I can have to say is constant. So I'm saying that the change of the concentration of the ONBR is 0. It is constant, it doesn't change in concentration. I am in a steady state of the reaction. I always have practically the same amount of intermediates. Now what is that change of the concentration of ONBR? Now there are ways how it is being consumed, and that is shown over here. So there is K3 times the concentration of ONBR times the concentration of aniline, C6H5NH2, and it is being consumed in that way, so it's negative for the change of the concentration of ONBr. And then there's also the way how it's being made. The aniline is made over here, and the ONBr is made over here in this step. So it is K2 times the concentration of H2NO2 plus times the concentration of the bromide. And this is a positive sign because here the ONBr is being made. So the change in the concentration from this portion of the ONBr is a positive number. Here it's being consumed, so the change is a negative number. And the whole thing is 0. So from this one here, I can then find what is the concentration of the ONBr. And then I can replace it over here. So the concentration of ONBr is then that I bring this one here over to the other side, and then I add a minus sign on each side, so I can forget about the minus signs. K2 times the concentration of H2NO2 plus times the concentration of bromide equals K3 times the concentration of ONBr times the concentration of C6H5NH2, and then I can divide by this and this, and I get a formula for the concentration of ONBr. ONBr is K2 times the concentration of H2NO2 plus times the concentration of the bromide divided by the concentration K3 and the concentration of C6H5NH2. And now I have a formula for the concentration of ONBr. I can plug this one in here, and I'll get over here that I have K3, and this K3 they cancel. ONBr, this one here cancels with this one here, so I'm really only left with K2 times the concentration of H2NO2 plus times the concentration of bromide. Everything else cancels. Okay. Now I have this formula, but this one here is an intermediate still, something I didn't put in. This is a catalyst where arguably I can control how much catalyst I have. I put the bromide in, I get the bromide out again, it's a catalyst really. But I could have controlled how much catalyst I have. So even though it's neither a reactant nor product, I have still some control, so I don't regard that as an intermediate. But what I do regard as an intermediate is this one. So, if this is an intermediate, then we say the change of the concentration of H2NO2 plus in time is 0. It doesn't change. Steady state. That is a steady state approximation. Now, what is the change of the concentration of H2NO2 plus? The change of that concentration is affected by this reaction, of course, where we are losing the H2NO2 plus, so it's a negative sign, times K2 times the concentration of H2NO2 plus times the concentration of bromide. And then we also have a loss of that in this backward reaction. If the reaction here goes backward, we also lose that, so we have minus K minus 1 times the concentration of H2NO2 plus. And then there is also one reaction which produces it, otherwise we wouldn't have it. This reaction here produces it, so we have a plus here of K1 times the concentration of H plus times the concentration of NO2 HNO2. Okay, so we have a nice equation over here now. We can solve this equation for the elusive concentration of H2NO2 plus over here, because that is what we still need up here, what we couldn't control. So, if that is the case, let's keep the stuff with H2NO2 plus on one side and move the stuff without H2NO2 plus onto the other side. And then we realize we have minus signs everywhere, so we will call it about minus signs. So we have K1 times the concentration of H plus times the concentration of HNO2 equals K2 times the concentration of bromide plus K minus 1 and the whole thing times the concentration of H2NO2 plus. Minus signs go away, this minus sign, and the minus sign, which we would have here, they cancel. Then this one here is taken out of the parentheses, giving K2 times bromide plus K minus 1 over there. Okay? Any question? No? Fine. Then I can divide by this one over here, and I get for my concentration of H2NO2 plus, then it is K1 times the concentration of H plus times the concentration of HNO2 divided by K minus 1 plus K2 times the concentration of bromide. Now if I have this formula here for the concentration of H2NO2 plus, I can plug it in over there. So I need to make myself a room that I can do that. So this one will then be K2. Is K2. Then this bromide over here. And then this one here becomes this one here. So we have a K1. And maybe I put my K1 over here. And then I have the concentration of H plus and the concentration of HNO2. And I divide that by K minus 1 plus K2 times the concentration of bromide. And I'll take this one here away, the Bartels cloud. Let's compare. This was the result I had from the rate determining step approximation. This is the rate I have from the steady state approximation. Is it the same? I have K2, K2, K1, K1. So it's both proportional to that. Bromide, bromide, H plus, H plus, HNO2, HNO2. So it looks very, very similar, this formula. The only difference is that here I have a K minus 1 plus K2 times bromide, and here I just have a K minus 1 in the denominator. So you get almost the same formula, except that it becomes obvious that I have in the steady state approximation also the dependence, an extra dependence here on the concentration of bromide. And then whether this is relevant or whether this is not relevant, that is determined how big is K2 times the concentration of bromide compared to K minus 1. If K minus 1 is much, much bigger, then it will not be changed by this one over here. And as a consequence, I'll have really the same formula. But if the concentration of my catalyst at times the second rate constant is actually sizable, then I will change that result. So the more the rate determining step is valid, the more this is really slow over here. The more this is really small, the K2 times bromide is really small, the more I get back to my steady state approximation. And the less this approximation is valid, the sizable this rate here is, the better the steady state approximation is, the more I need to include that portion. So, steady state approximation gives us generally better results. But you saw the kind of math I needed to do for the steady state approximation, and then before you saw me doing the very, very quick math for the rate determining step approximation. So, yes, you need to do more math, but you also get a better result out of it. There's another consideration, and that is, how do you really run your reaction? Does steady state make sense? If you run your reaction in a beaker, you put all your reactants in, and then you maybe heat it up and wait for your reaction to start, then maybe the rate determining step approximation might be better, because there isn't really a steady state. Because all your reactants are being consumed, intermediates might not even have time to build themselves up to a steady state. But if you run your reaction in a flow reactor, where you put the same amount of reactants into the reactor at all times, and extract the same amount of product at each time, then you certainly will build up a steady state in your flow reactor, and as a consequence, the steady state approximation is the one you want to use. So it depends a lot also on how you run your reaction. Do you do it beaker style in the chemistry lab? Do you do it reactor style in the production facility? Or anywhere in between. So what kind of approximation you want to use depends on the one hand side, how are the relative rate constants. If K2 is big, here, if there is no rate determining step, if there is no step that is much slower than the other steps, then of course don't use a rate determining step approximation. Only use it if there is a rate determining step available. Kind of curve. Now, these two approximations don't only stand by themselves. They are the underlying foundation for many further approximations in chemistry and biochemistry, in all fields that apply kinetics. So as soon as we are looking at enzymatic equilibrium, Michaelis-Menten equation and so on, which we are going to do next week, we'll find they're actually relying on what we have. But lastly, of course, the real way I suggest you're going to do all these kind of things is that you rather do the whole thing in Excel. For your Excel sheets, you then have again your index, and you have your time, and you have your concentration of, in this case, you would have your concentration of A and B and so on and so forth. And there is no reason why you could not have A, B, and C, and D, and whatever in here. So, in your homework, we have no B. So this is C. And we have the D. And we have an E. And E. And we have the G. And we have F. Okay. If we are looking at all of those things, then in your homework for A, C, and E, we have initial concentrations, and they were 0.3. 0.3. Then here was 0, and then here was 0.3, and then here was 0, and here was 0. And maybe I should just call them F and G, or G, F. Okay, if we have this one, then we can immediately figure out what is our rate for those reactions. So we need to have again dt, a time step, and let's put that to 0.1 here for now, give it a name, so that we don't have a problem with it, but then we can have okay, then we have these over here, and then we can figure out what is the change of the concentration of A. Now the change of the concentration of A, which we have over here, is that we have Ka, and now we need Ka, and the Ka over here is 0.3. Oops, I define this one. So let's go this Ka, and I need the K minus A as well, and the K minus A is 0.2. And then that is really all which governs our concentration of A, correct? So our concentration of A changes in the negative with the forward rate over here times the concentration of A, forward rate here, times the concentration of A times the concentration C, and it increases with the backward reaction which we have over here when the D is going backward over there, and so it is then positive with this one times the concentration of D that we have, and the whole thing needs to be in parentheses because the dA is of course depending on the dt, so I need to have times my dt. Okay, I know what is a concentration of A now. What is a concentration of C? The change of this one, that is the same thing. So let's see that it was defined as the same thing. Wasn't the concentration of A. So now it is the same way set up. And I can figure out what is the change of the concentration of D. And now when I need to look at the change of the concentration of D, I need to make sure that I figure out that if this reaction here proceeds forward, if that reaction proceeds forward, I actually use 2D's counters. So the change here for this reaction would be twice as big. I need to multiply that by a number of 2, which is 1. And then can set up all these kinds of reactions over here, and then I can plot it at the end. There is one complication in doing the whole thing. The one complication in doing this whole thing here is that we can have reactions which are vastly different in rate. We can have reactions which are really fast here, and reactions which are really slow. And the time step needs to be the right for that. If I have a really slow reaction, then I need to have a large time step so that I'm waiting for enough time that the reaction can proceed. But if I have really fast reactions, then looking at the slope at one point and extrapolating it for a long time will give me the wrong result. So the only solution which you have out of that one is take slow time steps, and having those slow time steps, keep on going and keep on going, and use more and more rows and more rows and more rows and more rows and so on and so forth. So if you're doing such integrations, it might easily be the case that you need to use thousands or hundreds or tens of thousands of rows in Excel. Excel can do 65,000 rows without a problem. So you can use many rows in Excel. And you might need to use many rows in Excel because otherwise the difference in time scales between the reaction will allow you not to integrate that problem. Ultimately, in chemistry, that's often a real problem, that we have so different time scales of our reaction that new theories are required in order to do that in a correct way. We're not going to talk about this in this class, like something which would be in medical school, but the point I'm trying to make is that knowing about the problem with the time step over here is something important, and getting around those problems is an active field of research. And with that, thanks so much. There's a homework we could do on Wednesday. I'm going to add homework on Monday to that. So maybe it's good to get it now. And again, make sure that you deal with this tool in the correct way. Okay, thanks.